Hey everyone, today we're jumping into a tool that helps us measure the unmeasurable and, some of the unsummable. It's honestly one of the most powerful ideas in all of mathematics, and we're going to break it all down together. Let's dive into the definite integral. So, it all kicks off with a really simple question that, believe it or not, you can't answer with a ruler. Finding the area of a square or a triangle? Easy, we learned that in grade school. But what about a shape with a curved edge, like this one? How do you get a precise measurement for that? And this isn't just some abstract geometry puzzle, right? It's a problem that pops up absolutely everywhere. Trying to calculate something that's always changing is really the heart of calculus. And it's exactly where our simple formulas just don't cut it. Okay, imagine you're tracking a car's speed over time. It's speeding up, it's slowing down. Its velocity isn't a nice, clean, straight line. It's a curve. So how on earth do you find the total distance it traveled? Well, it turns out the distance is exactly the area under that velocity time graph. But there we are again, staring at the same old problem. How do we measure that curvy area? This is where the real genius comes in. If you can't measure the complex thing directly, you do the next best thing. You approximate it with simple shapes you can measure. And the shape of choice? The good old humble rectangle. This is the core idea behind something called a Riemann sum. Let's go back to our car. First, as you can see, we just slice that whole area up into a bunch of skinny vertical strips. Now, if you zoom way in on a very, very short sliver of time, the car's speed is, well, it's almost constant, right? So for step 2, we can just pretend that slice is a rectangle. The area of that little rectangle, velocity times time, gives us the distance traveled in that tiny moment. And finally, step 3, we just add up all those little rectangle areas to get a pretty good estimate of the total distance. Now, as you can probably see, our method isn't perfect, at least not yet. If we use the left edge of each strip to set the rectangle's height, like on the left, you can see we're leaving out some little bits of area. We're underestimating. But if we use the right edge, like on the right, we end up including a little extra area that we shouldn't. We're overestimating. So they're good guesses, for sure, but they're still just guesses. So how do we make it perfect? This is where we make the huge leap from a pretty good approximation to absolute, perfect precision. We're going to take our rectangle strategy and just push it to its logical extreme. Just think about it for a second. As we slice that area into more and more rectangles, each one gets narrower and narrower. Those little bits of area we were missing, or the extra bits we were adding, they get smaller and smaller and smaller. So what if we let the number of rectangles shoot off toward infinity? The width of each one would shrink towards 0, and our error, that little curvy bit we couldn't account for, would just completely vanish. And that incredible idea has a name and a symbol. This is it, the definite integral. Now, I know that symbol can look a little intimidating, but trust me, it's just a fancy way of writing sum up an infinite number of impossibly thin things. That long stretched out S literally stands for sum. The f of x is the height of each rectangle, the value of our curve, and that little dx, that just represents that infinitely small width. Put it all together, and you get the perfect exact area. Okay, so we have a way to define the exact area. But actually summing an infinite number of rectangles? That sounds impossible, right? And for centuries, this was a massive roadblock. Then came one of the biggest breakthroughs in the history of science, a discovery that connected two ideas that seemed to have absolutely nothing to do with each other: area and slope. You see, on one side of mathematics, you had integration, this whole problem of finding area under a curve. And on the complete other side, you had differentiation, the problem of finding the exact slope or the instantaneous rate of change at any single point on a curve. For the longest time, everybody thought these were two completely separate problems. This equation right here is the answer. It's the fundamental theorem of calculus, and it is a jaw-dropping, game-changing shortcut. It says that to find the exact area under a curve from point A to point B, you don't have to sum infinite rectangles at all. You just need to find a new function, we'll call it capital F, whose slope, or derivative, is your original function. Then you just subtract its value at A from its value at B, and that's it. So the huge takeaway is this: finding an area and finding a slope are inverse operations. They undo each other, just like multiplication and division do. This single realization changed everything. It turned an impossibly hard problem into a surprisingly simple calculation. But we don't have to stop there. Once you have a tool this powerful, you can start tackling even more interesting problems. Like, what if we want the area not just under one curve, but the area trapped between two different curves? The big idea is actually pretty similar. Instead of our rectangles going from the curve all the way down to the axis, we can just imagine them stretching from the bottom curve right up to the top curve, perfectly filling the space between them. And the logic is exactly the same. The area is just the sum of all those infinitely thin rectangles. But now, the height of each little rectangle isn't just the function's value. It's simply the value of the top curve minus the value of the bottom curve. We integrate that difference, and boom, we get the exact area of the region between them. It's such an elegant and powerful extension of the same idea. So we've gone on this whole journey from a simple question about curvy shapes all the way to a profound theorem and its cool applications. But why does all of this really matter? Why is the definite integral one of the most important ideas ever discovered? Well, it's because almost everything in the real world involves continuous change. The integral lets us take a constantly changing quantity, like the velocity of that car or the energy in an audio signal or consumer demand in economics, and find the total accumulated effect. It's the mathematical engine running behind modern physics, engineering, economics, medicine, and so much more. Ultimately, the definite integral gives us a framework for solving problems that seem totally impossible. It teaches us this really powerful lesson. You can break down overwhelming complexity into an infinite number of simple pieces and then reassemble them to find a perfect whole answer. So the real question is, now that we have this power, what are we going to solve next?